Yes?
We're not going to have to like draw two-dimensional curved shapes, are we?
Oh, yeah. But relatively straightforward ones. The stuff we require you to draw in Calc 3, it's the type of surfaces and curves that you learn to do calculus on. So they're necessary for learning. Later on, you can use a computer to draw stuff. But to learn, to really understand derivatives, partial derivatives that we'll get to, and double integrals and triple integrals, yeah, there's something called a triple integral. You need to be able to draw pictures. So a sphere is going to be the first curved surface we look at in this class. The definition of a sphere is the set of all points equidistant, same distance, from a center point, just like a circle, except now we're in space, so it creates a surface instead of just a curved circle. It seems to me, then, that we should be able to come up with the equation of a sphere based on the same argument we use for the equation of a circle. Now, I'm not going to draw a sphere for the argument, but if you ever want to draw a sphere, it's not that bad. Whoa, that's weird. It's still on highlighter, yeah. We're still, yeah, I'm going to draw the eclipse for you. I was gonna think of a good problem for the eclipse because you guys just had Calc 2, and I could imagine some polar coordinates, finding the area as part of the sun. But I have a 5-year-old son, and I didn't have time. I didn't have time to think up a good problem.
We didn't either.
Yeah, you didn't either. Well, but you just got done with Calc 2. If you ever want to draw a sphere, it's really easy. I guess this would be like your prime meridian if you want to compare it to the globe, and then draw an equator. Right? And then you have your happy little sphere, right? But for this little derivation, I'm just going to take the circle, pretend like it's the cross, it's either the equator or the prime meridian or a great circle, it doesn't have to be either one, of the sphere. So that this point right here, let's call it, I don't remember what I called it in the notes, H, K, and I don't know, L, sure, why not? So that's the center, C for center. So imagine this being in 3D. And then the radius would be this distance to the edge of the sphere, or in this case the circle, call it R. And then that's going to be the same no matter which point you pick to draw the radius to from the center, right? So we could think of this point as varying, x, y, z. So what would be the equation of a sphere? Well, think of the distance formula squared, using one point as your center point as like x1, y1, z1, and x, y, z as the other point, x2, y2, z2 if you like. Fill in the distance formula, but square it. So what does the distance formula normally say? It normally says d, and I'll put the d on the right side. So it normally says d is equal to, let me use this notation. Delta x squared plus delta y squared plus delta z squared, right? Whoops. But square both sides. Okay. We can do that. And we get that, right? Okay, now what would be the change in x between the center point and this? So the center point is fixed, but this is like a variable point. That can vary. So what would be the difference between the x values? The way we normally would write it is x minus h. And then we square it. That would be like delta x squared. What about delta y? Y minus k. And then delta z. Don't forget to square y minus k. And then delta z. Z minus L. And then what is D in this case? R, the pirate would say. And so this would be your standard equation of your sphere. Remind you of anything? Looks just like the standard equation of a circle, except one more term, right? Very nice. And in fact, this derivation is the same derivation except for the extra term that I would use to derive the equation of a circle. So if you plotted points, what I'm saying, you'd maybe want to use a computer to do it, but if you plotted a bunch of x, y, and z values they would lie on the sphere if you graphed it. All right, so that should hopefully be easy enough to remember based on your previous knowledge. So you guys look at this problem. Tell me, what's the center and radius of x minus 2 quantity squared plus y plus 5 quantity squared plus z plus 2 quantity squared equals 25. So C for center. What's the center? 2, negative 5, and negative 2? And then what's the radius? 5. Is it really that easy? Yes, it's really that easy. I feel like I'm selling you a food processor. It is really that easy.